Hey guys, back again. Excuse me, problem number 9, 7 marks. I went ahead and did step 1 and step 2 for this math induction inequality, showing that 2 to the n factorial is greater than or equal to 2 times n factorial is greater than or equal to 2 to the n factorial times n factorial squared for all n in z plus. Okay, so I proved true for n equals 1. I'm assuming true for n equals k. I'm going to use that in step 3, where I prove that n equals k plus 1. For n equals k plus 1, when k again is in z plus. Okay, so I'm going to use a string of inequalities. I want to prove that the following is true. I want to do this slightly differently. Okay, is greater than or equal to 2 to the k plus 1 times k plus 1 factorial squared. That's a whole lot of stuff. Okay, I'm going to take this, and through a sequence of inequalities and entirely built on inequalities, or actually equalities and inequalities, I will show that that's true. So I'm going to take this left side, which is 2, and actually I'm going to do a quick morph of this thing and call it 2k plus 2 factorial. All I did was distribute that. Well, that's going to be equal to, by a definition of factorial, 2k plus 2 times 2k plus 1 times 2k factorial. Okay, so I'm going to bring that along to the next line here. 2k plus 2, 2k plus 1, and then 2k factorial. All right, what I do know from step 2 is that this expression will be greater than or equal to, I'm not going to change anything with the first two terms, and leave those as 2k plus 2 and 2k plus 1, but based on step 2, 2k factorial is greater than or equal to 2 to the k times k factorial squared. So I'm going to replace that with 2 to the k times k factorial squared. You can see that that is greater than or equal to that. Therefore, those two expressions follow suit. Okay, now I'm going to bring my new expression. I'm going to write this in blue, and I'm going to factor this 2 out of this first term, and I'm going to tack it on to this 2 to the k. So if I take this 2 out, the first 2 right here, this becomes k plus 1, then I have 2 to the k plus, or 2k plus 1. Then I'm going to bring this 2 to the k out in front with the 2 that I pulled out right there, and that will be 2 times 2 to the k, which I could rewrite as 2 to the k plus 1. Okay, I'm starting to see pieces of what I'm trying to show start to show up. Okay, and then of course I've got k factorial squared. Okay, I'm going to use another equality here, and this will be equal to, leave the 2 to the k plus 1 out front. I'm going to leave the k plus 1 right here, but then I'm going to split these two. It's k factorial times k factorial. I'm going to put a k factorial here, then 2k plus 1, then the other k factorial there. Okay, so those two expressions are equivalent, and now I'm going to continue with an inequality. So I'm going to rewrite on the next line. Okay, after rewriting that, if you look closely here, what you're going to see by definition is that that is equal to, in blue there, is equal to k plus 1 factorial. All right, so let's rewrite. This is going to be 2 to the k plus 1, k plus 1 factorial, and then I've got this expression here, 2k plus 1, k factorial. All right, so just think about where we've come from. We've come from trying to show that this is greater than or equal to this, and I have not done anything on the right side here. I've just taken what's on the left side, this expression, and I've just continued to show through a string of equalities and inequalities that currently, right now, this is greater than or equal to this. Okay, and I'm going to turn this, somehow relate it back to this in the next step. Okay, so I've got 2 to the k plus 1, k plus 1 factorial. Okay, if I wanted the expression that I have up here, I'd have to have that squared. Okay, but I don't. I have this, 2k plus 1, k factorial. But because 2k plus 1 is greater than or equal to k plus 1, I think we can all agree to that, then 2k plus 1 times k factorial would be greater than or equal to k plus 1 times k factorial. And this just happens to be k plus 1 factorial. Therefore, this expression, right, 2 to the k plus 1, k plus 1 factorial, I have not changed anything, but this expression underlined in green is going to be greater than k plus 1 factorial for these reasons down here. All right, and what I've now shown is that I'm kind of skipping through all of this stuff. I shouldn't have wrote it there. But this, all the way down here, keep going, is going to be equivalent. I should have erased that and made equal sign there. This will be equivalent to 2 to the k plus 1, and that's k plus 1 factorial squared. Okay, so I have done all of that by just manipulating the left side using what I know in step 2, as well as just other algebraic properties. Okay, therefore, since this is true for n equals 1 and n equals k plus 1, then it is true for all n in z plus by math induction. Okay, so I do not need to, at least right now, I'm not going to write out that statement. You know what that should be. But this is about as complex as it gets algebraically. There are some math induction problems that involve using the derivative. But this is one of the heavier math induction problems. So if you got any questions, again, shoot me a message and let's chat through it and get her done. So, all right. Yeah, see you next time.